Good morning.
Good morning.
Everybody survived the night, survived the test. Let's see. We are about to take this to another level in a good way. Let's see. Don't think I want to say anything about the test just because everything is kind of random depending on who you are and how you did, but I would very much like to talk to you about it one-on-one. As I always say in my classes, I would encourage you to argue with me about it in a friendly way. If you think you deserve more points for something, I doubt you'll argue with me if you think you deserve less, but you're welcome to do that too, I guess. So I tried to be pretty thorough in what I said back to you on my grade. So hopefully you understand or learn something from that. Is there anything you want to, I don't know, ask about it? I mean, it can be particular to yours, just because, and the reason I'm opening this up is because it might be helpful for other people too. So I feel the need to stare at it for just a second before we launch. Just give you a second to think. Stare at the key. Let's see.
Thought it was all good, but the time that it was due kind of threw me off.
That felt tight.
Well, I've only had one other math teacher, well, two others, and for online, what they do is they just say you can turn it in at any time by the end of the day.
If there's you're more than welcome to make a request of me on a particular day. I mean, I just think of this as being like a class time, and so this is the time we usually meet. So given the
Okay.
test we usually do, but if you're like, on a particular, and I had a couple of people do that, say, oh, I got to work, and I usually listen to the video, and so can I take it from 3 to 5 or whatever? And it's like, whoop, the answer to that's going to be yes.
Cool. Okay.
So yeah, feel free to ask.
Sweet. Thank you.
I'm pretty reasonable. Yeah, I don't think there's anything I'm going to say. Now it gets interesting. Now this is going to go somewhere that is just rather surprising, and I'm always incredibly troubled by how books explain this, and so I'm gonna probably do this sort of very differently, because I really want to give us time to kind of soak on it and understand what is probably the most amazing idea of this whole concept. I mean, what this exists for. And so I don't know, we'll figure it out a day at a time, but let's launch into this. So 11.1, which I just turned on in my open math. 11.1 is there now, and according to your syllabus, we're spending a couple of days on this. 2 days, today and tomorrow, and then I might even not assign 11.2. We might even keep going. So anyway, think of this as rather introductory, but I'm very interested that you understand this deeply. And if you read this in the book, you will not understand it at all. I shouldn't say all of you, but most of you. I would say I wouldn't. So I want to show it to you a lot more simply and a lot more beautifully, and kind of try to give you time to soak on it a bit. So 11.1, chapter 11 is ultimately coming down to approximating. This is an amazingly useful. approximating equations or functions with polynomials. And what I'm talking about here is we have all kinds of functions that we're aware of, like natural log and sine and cosine and tangent, and then rational functions like 1 over 3x squared, things like that, that cause these asymptotic sort of graphs. We have all these different kinds of functions we've looked at, and it turns out this section will show that we can approximate these with polynomials. And we love polynomials. Remember, polynomials for derivatives were so easy. Remember taking the derivative of sine? Like, how in the world are we going to do that? Polynomials are really easy to take the derivative of and the integral of, and they're also easy to kind of type in. Like, you don't even need sort of a fancy calculator, sort of back in the day when people didn't have all this stuff. So the fact that you could replace cosine and say, that doesn't even exist, we'll just write it as a polynomial. Unbelievable. So I want to kind of lead you into that amazing world. But first, let's remind ourselves of something that we studied last section, and this is one of the payoffs of last section. Again, last section was rather theoretical in the sense that we were looking at, will the series converge to something and so forth. And we're going to make huge use of that in this section. And probably this section will help you understand at least the reasons for and the purpose of the previous section. So let's dive in. So for instance, one of the things we said in the last section that was really important, and this is what the first question on the test was about, is if you have a series that looks like this, some constant in front and then some ratio, which again means, okay, if r, and notice it starts at 0, it's really important. So this would be a times r to the 0, r to the 0, that would be 1. And remember, we're thinking of r as being some number that's less than 1, because remember how that as a geometric series wouldn't converge unless that r was less than 1. It made each term get smaller, smaller, smaller. And so then the next term would be, well, a again, because a is every one of them. And then it's r to the first, and then a times r to the second, and so on and so forth. And so this went on forever. And we said that would converge to something as long as r was less than 1, technically the absolute value, because it could be a negative 0.9 as well. So maybe I'll throw that in there. And so and I want to build this again just really quickly. Many of you did it this way on the test. If I said, okay, that sum is equal to, well, that whole statement, and then we took that same statement. I've built this for you more than once, but since we're seeing that, oh, it's geometric, look, because every one of them is multiplied by r. That's how you're getting from one to the next. If I say times r, yeah, that gives me that one. If I say times r, yeah, that gives me that one. Geometric series, that's what makes it geometric. So we say, cool, that's how I'm going to find the sum of it. If I take r and multiply it by both sides of this, I get the same exact sequence again, right? Or the same exact series, you might say. And so then if we came back and said far out, let's subtract these two things, then I'd have Sn, the sum of the series. That's what we're after. We'd like to know what Sn is, minus r times Sn. And then we see that a whole bunch of these things just cancel out. And it sort of cancels forever. And so all you really have is left is a on that side. And so if we factor Sn out, leaving 1 minus r. Whoa, what am I doing? If I factor Sn out of both of those, then we get the amazing formula that you can add up that infinite series and get the exact answer. That's an equal sign, not an approximately equal sign. Again, because this is geometric, this is very important. That's what we're going to focus on in this section alone, is just geometric series. Not alternating, not telescoping, not all those other ones with factorials and all that kind of stuff. just the geometric series. And so we said that will be the sum of it. And we said that's true, again, as long as that R value is less than 1. Now, I want to introduce one kind of new term that we'll be using a little bit today, but we consider 1 to be the radius of convergence, that term radius. And keep in mind, it also means since the absolute value of R is less than 1, another way to say that is just that R has to be between 1 and -1, right? This is called the interval of convergence. And so we're saying, yeah, this is awesome. And this really does converge and equal something. And you can even find out what it is and get the exact right answer. The first question on the test, you should have got 36, the exact right answer for infinitely many terms added together. And we have a formula to do it, but that doesn't work unless R is between 1 and -1. Well, do you see why they use the word radius? Because it's kind of like zeros in the middle of this, and then if you radius out 1 this way and you radius out 1 that way, then you're 1 away from both sides. And so it's kind of like a circle illustration, if you will. That's kind of where that language comes from. So radius of convergence. Let's see, I didn't get the whole word in there. Are you good with that? Are you?
Yep, that's looking good.
Huge foundation for what we're doing in this section. So let me show you something amazing. So now what we're going to do in this section is not so much to think of R as just a number, but we're really going to do this. If I write something called a power series, this is new, deserves to be read. A power series is a geometric series except we're going to replace this R with an X so that this thing ends up being really A times 1, because when X is raised to the 0, it's 1, and then when X is raised to the 1, it's X, and when X is raised to the second, and so on and so forth. Again, ... meaning it never ends. We're going to take advantage of that fact to recreate some things. And so what we did in this last section is we said, okay, cool. If we have something like this, and this was your first test question, again, a little bit in disguise, but you took in this last section, kind of in 10.1, we took that statement and we said, hey, that's the same thing as A over 1 minus X. We went that direction in chapter 10, right? That's what you did on your first test question. You said, hey, that turns into 36. That's cool. That's a geometric series. All we're going to do in this section, boom, go the other direction. That's it. This is what chapter 11 really is. Now, let me show you what I mean. I think an example will warrant itself well here. Let's consider f of x, some function equal to 4 over 6 plus x. And you know what that looks like. If I go to Desmos and I make a graph of it, y equals 4 divided by 6 plus x, or x plus 6, doesn't matter. again, you get that asymptotic thing, and perhaps you're not surprised that it goes crazy right around -6, because if you put x is -6 in, you get 0 on the bottom. So you end up with 4 divided by 0, which is really 4 divided by 0 is really infinity. And that's why the graph just kind of goes, takes off right around -6. And so hopefully you're used to rational equations looking like that. And so what we're going to try to do is come up with a polynomial that looks exactly like it. It's exactly the same graph. Well, kind of. What do I mean? Well, would you agree? This looks an awful lot like that expression right there. Like if I mess with it a little bit, couldn't I get it to look just like that? It's such a beautiful and a simple concept. Okay, well, notice there's a 1 there and I got a 6, right? That's not good. I need a 1. And then I also need a minus sign. So it's very important you stare at this expression and say, okay, well, I can have any number on the top I want. I don't care if that's a 10, -16, 1/3, I don't care. But I need a 1 here and I need a minus something there. I need a minus x there. So the question is, can we get this to look exactly like that? Well, let's do it. Let's see. Well, if I needed a 1, couldn't I divide the top and the bottom by 6? So I'd have 4/6 over 1 plus 1/6 x if I divided by 6. You agree with that? And then I could say, so I guess I could say then that f of x is equal to, I guess that'd be 2/3 on top. And now I got a 1, and then I could make a minus, but then this would have to be considered -1/6 x, or x over 6. I guess it doesn't really matter how I write it. Do you agree it kind of looks like it's in the right form now? Okay, well, then couldn't I, as I mentioned up here, then go this way with it and like rewrite it as a summation symbol, or rewrite it now as an infinite series, as an infinite geometric series? So the only thing that's really different is I just have, well, I don't just have x, I have 1/6 x, and it's negative. So what? Well, if that's true, then f of x, it's time to switch colors. Then f of x could be called, let's see if I can stare at this summation up here and rewrite it. So a is in front. Okay, a is 2/3. All right, I can handle that. A is 2/3, and then it's x to the n, except for what's my x? Well, it's -x over 6 to the n. Is that it? Is that right? Is that all it is? Well, if I let n be 0, like what would this expand out to? Because that's kind of a weird way to write it, right? I mean, mathematicians love stuff like this because it's real compact, but what does that actually mean? Well, if n was 0, that'd be x over 6 to the 0. Anything to the 0 is 1. So then the first term would just be 2/3. And then I'd have n equals 1. And let's see, what does that become? Well, I'd still have my 2/3. But now I'd have -x over 6 to the 1. And then I'd still have my 2/3, and I'd have -x over 6 to the 2, and so on and so forth. So that's okay, right? That's not bad. And it's a little weird looking, so maybe let's clean it up a little bit. Like 2/3, and then 2/3 times 1/6 is 2/18 or 1/9. And then the next term, well, it'd be -x squared. So that become a positive. And so notice this is creating an alternating series because I have a negative and it's being raised to the 3rd and the 4th and the 5th. So it's going to plus minus plus minus. That's why we spend some time with alternating series so that you cannot panic about that. Let's see. And then I'd have 36 on the bottom. 2/3, 3 times 36 is 108. 2 divided by 108, that'd be 1 over 54. So this is, the fraction is 1 over 54, and it'd be x squared. And then the cubed term, 3 times 6 cubed, quit. 3 times 6 raised to the third. 648 divided by 2. I think I'm getting this right, 324. So my next term would be 1 over 324 x to the third, and so on and so forth. So do you understand what we're saying here? I mean, do you understand the profundity, if I might be so bold? We are saying that these are actually equal. We are saying that the fractional equation, the ridiculously strange shaped rational equation, is actually equal to what we just wrote. Surely that cannot be true. Wow, all this time I've been seeing copy paste and I just saw the word duplicate up there that I've never bothered to read. That's what we're saying. I mean, don't you find yourself going, what? There's no way that's equal to a polynomial. Remember what polynomials look like? Don't they look like this? Like there's a cubed equation, and fourth degree equations kind of look like that, and fifth degree equations might look something like that. Remember, so it's like, how can that possibly look like? Well, you know, this one over here looks something like that. How can those look the same? Well, that's where I'd like to start kind of playing a little bit here and let you watch this happen. So I got to take a quick picture of that so I don't forget it while I go over to Desmos and type it all in. So, okay, we're over here in Desmos, and so let's watch this happen. So our equation was, well, first y equals, I already forgot, pictures, boom, boom. Oh, that's right, 2/3. Well, notice that doesn't look anything like it, but what if I add one more term? The next term was minus 1/9 x. Do you notice it's trying to look like it, if you will? Do you see how it's growing to look like it? Now notice this is an important concept. Notice, where does it look like it? Well, it looks like it at 0. Do you see how it's trying to imitate it, how it's behaving at 0? So it didn't do bad, if you think about it. I mean, if I back up and get rid of this, it didn't do bad. If it only has a constant term to work with, it didn't do bad there. It looks just like it, at least at 0. It has the same exact answer, right? But that's a little better. Notice now it not only has the right answer at 0, which apparently is 2/3, but it even has the right slope now. You see how that kind of improved it? It's like this line, and we'll go into this more in detail later on, but you may remember this from calc. I think it was chapter 4 where we did linear approximation. We tried to find a line that approximated an equation. Well, we just did that. I just found a line that approximated that curve right there. In a sense, you've done this part of it before. But the amazing thing here, we're not done yet. We're going to keep on going and approximate this, not with a line, but with a parabola. What was the next term? I don't know, I forgot. 1/54 x squared. So if I add 1 divided by 54, boom, x squared. Notice now it's even looking more like it. Notice how it just, like, if you're really close, notice you can't even tell the difference. And that's only a parabola. Like, we're a long ways from infinity right now, right? Then we have a cube, a fourth, a fifth, sixth, seventh, eighth, ninth. We have thousands of terms to add to this. That it already looks exactly the same as long as, well, as long as I stay between 1 and -1, right? Remember that radius of convergence thing? So, okay, well, let's keep going. Our next term was minus 1 over 324, minus 1 divided by 324, x raised to the third, even more like it. And let's see if I can sort of, and this is the advantage of sigma notation. If you remember what our sigma notation was, wasn't it 2/3? It was always 2/3. So my next term is plus because I'm not figuring this out this time. I'm just saying 2/3. And then down there on the bottom, there was a 6. And it was raised to whatever power we were at. So we're at the 4th term right now. In other words, there's the coefficient in front of this. Do you understand that? Isn't that what I was doing a second ago? And then I hop out of there, and now I'm at x to the 4th. You see how it's getting better and better and better? Like it's just looking better and better. This is very exciting. So if I was, I'll do one more term, then I'll quit. So then it would be minus 2/3 again, except for down there, it'd be 6 to the 5th times 6 raised to the 5th. And now we're up to x to the 5th. And so it just looks more and more and more and more like it. Now, do you agree? First of all, that's a 5th degree polynomial. So doesn't that look, and notice it's got a negative exponent. Do you remember from Math 111 and maybe some previous times? Isn't that what cubed equations look like? Or I'm sorry, 5th degree equations look like? Come on. Is the blue curve ever going to look exactly like the red curve? The answer to that is no, it's not. Like a polynomial can't look like that. And this is what this convergence thing is all about. Would you agree it looks amazingly like it? Well, between about -3 and +3. But I can't, if I want to say those are equal, I couldn't go to the red graph and like throw in x is 15 and then go to the blue graph and throw in x is 15. They're not going to give me the same answer. Like it would give me about the same answer as long as I hung out around between 3 and -3. That's what the radius conversion thing is all about. Now, the idea here is, though, you can get it to look as much like this as you want, but they're not going to be equal, at least not in this case, because the radius doesn't allow it. There are problems where there is no radius. Like there'll be an equation that looks exactly like sine. You can put anything you want in. It's identical, same exact graph. Because polynomials could be made to look like sines and cosines. But this has a radius of convergence. In other words, it has a limit. You can't just put anything you want, right? Isn't that what we've been talking about? So let me get a decent shot of this to throw it in the notes.
Is it ever going to copy over the stuff that's at the negative y-axis?
Yeah, like what about the rest of that graph over there? And that's the answer to the question is no. Like it's never going to be over there on the left side. In other words, the business of where does it look, where does the blue graph look like the red graph? The answer is around 0. Does that make sense? And so we'll be playing with this. This is what this chapter is about. So it looks like it around 0. And in this case, because the red graph is 2 different graphs, that means it's never going to look like the other one. There we go. So it's kind of cool, but there's also things that maybe we not happy with. So we'll be looking at other graphs where we'll be happier than this one. But really the key is these really are, they really are the same. Well, around x is 0. They're behaving identically around x is 0. Now, I want you to think about something, though, that happened in this particular problem. regarding the radius of convergence. Does it make sense? Our problem, and this is a really important kind of concept right here. Does it make sense? That thing right there, well, if I look back up here, this thing right here, that X value had to be less than 1, right? In other words, the junk that is being raised to the nth power has got to be less than 1. Well, notice in our case, what junk is here? Well, here we have X minus or X over 6. So with respect to our radius of convergence, X over 6 has to be less than 1, which really means X has to be less than 6. In other words, I said it looked about the same. Did you agree it looked about the same out to maybe here, which is 4, and here, which is -4? You agree with that? I'm saying it looked about the same between 4 and -4. Well, the right answer to this question is actually 6. How come it doesn't look the same at 6? If it's supposed to converge, if they're supposed to be exactly the same out to 6, how come it doesn't look the same at 6?
Because we still have more terms to go.
Yeah, you only have 5 terms here. You got way more terms. If you have infinitely many of them, then they're going to be identical. But only if you stay between 6. And so this particular problem, then, these are equal, if you will, if and only, have you seen this language before? If and only if X stays between 6 and -6. So you'd say the interval of convergence. In other words, we can make these look identical, but we got to stay inside 6 to do it. Now, maybe you can see why, because notice this asymptote over here at -6. We need our blue graph to get steeper. We can get that blue graph to lay against the red graph there, but we can't go beyond 6. Notice the asymptote even kind of shows us that, yeah, we're not going to get past that. So if you went into Desmos and just kept adding more terms and more terms and more terms, you'd get it to just look more and more and more, well, like the right side of that graph, except it's only going to look like it between 6 and -6. That's what the radius of convergence is all about. Let me show you this in another context. Where's my Excel? I just said yes, I want to see. Been behaving obnoxiously lately. Okay, so here we are. So we said here, our original equation, again, I want to just go slow here. Our original equation was 4 over 6 plus x equals 4 divided by 6 plus x, right? That was our original equation. And so that allows us to plug numbers in. Well, let's plug a number in. Let's plug in, I don't know, 3. Okay, well, I can't really use x. I got to use that location up there. So would you agree if I, have my function here, 4 over 6 plus x, and I plug a 3 in, see how the answer to that is 4, 4, 4, 4, 4. It's 4 ninths, right? So the question is, will the other one give us the same answer? You understand that? If we add up all of those polynomial terms, remember we got to add them all up, will we get the same exact answer? Well, let's do that. Didn't we start at n was 0, and then we went 1, and then 2, and then 3, and then 4, right? And here's where the sigma notation is huge. Sigma notation is huge. I'm going back to it. It said 2/3 times x negative x over 6 to the n power, right? 2/3. So it was always 2/3. So each term was 2/3, and then it was times x over 6, except that was negative, and it was raised to the power of n. But n was this term over here, right? In other words, isn't this the n? I put a label there. Isn't that our n? So it was raised to the n power. So instead of saying raised to n, I'm going to say raised to that number right there. And then again, x is the number I'm happen to be plugging in. What's the number I'm plugging in? Well, that 3 right there. I'm plugging the same number into both of them. So, you know, are they equal right now? No. But that's because this only has one term. We need more terms. So I always want it to use that when I copy it down. I'll just do that. So nothing changes. But now I drag this down and find the second term. So the first term in ours is 2/3. And I had that written out at one point. And then the next term was minus 1/9 x, right? Minus 1/9 x. Well, if you plug in x is 3, isn't minus 1/9 times 3 minus a third? You see it working? Like I'm plugging in x is 3 right now. So notice what the sum is after first two terms. The sum is supposed to be 0.444, and yet down here it says the sum is 0.3333. Why are they not the same? Because I only have two terms. This is a line. Now you may remember from Desmos, wasn't I 3 is a long ways away from where they matched up perfectly at x is 0. 3 is a long ways away. If we went to 0, then it'd be better, but let's go back to 3. So if I just add more terms to this, first of all, I'd like you to notice, what are the terms going towards? What do you notice about the terms? This is a geometric series. They're going to 0, which is a good thing, right? Because if we're going to add those up and get something, then they better darn well be going to 0, right? What do you notice about the sum down there if I add them all up? Again, you told me before you can see that, right? It's not so small you can't see it.
It's visible.
Notice it says 0.4444, like it's working. Do you see what I'm saying? They're the same thing. Well, as long as I pick x as 3, will be the same thing if I pick x as 4. Yes. Notice it's supposed to be 0.4. Notice it's about 0.4. If I put 5 in, are they the same? When I put 5 in, the right answer is 0.363636. What do we get? We get 0.3649. Notice it's not quite as good. Why is it not quite as good?
Because it's getting closer to the radius of convergence.
I wish it could be said better than that. It's as soon as we get closer and closer to 6, you saw it deviating on the graph, right? We just need more terms. Well, notice I have a lot of terms here. I have 30 of them on the graph. I mean, I only had like 5. I got 30 of them here, and it's still pretty close, right? And can you see that these terms are going to 0, but not as fast now? And so if I added more terms though, wouldn't I be able to get this to look better? I mean, in this case, these aren't near as 0-ish as they were a minute ago. Like when I stuck 4 in, notice that last term down there is really small. It's 0.5 zeros and then a 3. It's really small. Well, if I get out here to 5, well, now all of a sudden that's not quite so small. Now it's only 2 thousandths. It's still pretty small. But if I wanted to keep going a little bit, notice now they're pretty small. And so now what does it add up to? So now I have like 60 terms or whatever it was. What does it add up to? It's supposed to be 0.3636. Look at that. It's 0.363636. So the key is infinity. Does that make sense? Can you appreciate if I go to 5.8, now we're getting really close to the line, to the radius. And so notice what happens. Are these on their way to zero still? Yes, but notice how slowly they don't want to go to zero very badly. I'm down here 64 terms and it's still 700ths. Like that's not zero yet. Are they still the same? Yeah, but you actually need all billion terms for them to be the same now. I need more terms. Now here's the interesting thing. What if you bust outside of this and go past 6 to say 6.1? What do you notice about the terms over here? What do you notice about these terms?
Are they increasing?
They're actually getting bigger. Do you see that? Notice it's not very fast, but notice they're actually getting bigger, bigger, bigger. You have no hope of that adding up to something. You understand that? They have to get smaller, smaller, smaller. That's the divergence test. Those terms are not getting smaller, smaller, smaller. So this is not going to add up to something now. I'm not getting zero. Not only am I not getting zero, they're not even getting smaller. It's not even ever going to go to zero. And if I, blow way past 6 to 8, notice now you can see they're getting bigger really obviously. It's like, oh, that doesn't work. Do you see what the concept of radius of convergence is? In other words, these are an exact match, but bad news. You got to hang out between 6 and -6. They're equal, but you can't plug in any numbers outside of 6. Now you should agree with me that it's like, well, that's a pretty strong limitation. If I'm using this for something, it would be nice to be able to plug anything in, right? And so what I said before is true. We're going to get to a place where we have some equations don't have a radius of convergence. In other words, it's infinity. You can plug in anything you want and you'll get the same answer for both equations. How's your brain? Are you taking that in? Are you seeing it? Are you visualizing it in Desmos that they really do look the same between 6 and -6? Well, at least reasonably close. But I can see it a lot more here, right? Because I just added 64 terms now. That's 64 terms to it. And not only that, I plugged something in. So it would just take me too long to type all that into Desmos, right? But I could add 62 terms and they would look really good. It would look just better and better. And you saw them looking better and better and better the more I added terms.
Hey, Doug, I have a question. In some other classes I've had, we can do fit lines in Excel, and we were told to like stay away from the polynomial fit lines because they could literally be changed into anything. So I'm wondering why we have a limitation here, but in Excel, it can just fit anything.
Yeah, the problem with Excel is you're putting in a limited amount of data and you're trying to find in a curve that'll follow it. And if you have 6 data points, and maybe they're roughly curving up like this, but it's kind of a little bit jumpy. And so you say, let's find a 6th degree polynomial. Rather than it following it kind of smoothly, but somewhere between all of them, it actually just makes this gigantic up and down, huge undulations hitting all 6 points. But it's like, that's not modeling the data at all in terms of predicting the future. I don't know if that makes sense, but.
Kind of just seems like our class here is very limited, and then it seems like Excel just kind of like has unlimited potential for polynomials.
Yeah, it actually does. But notice in our case though, we have crazy coefficients in front of these things, and then we're going to see in a few sections that you don't even have to have every term. In other words, our particular one had every term. It had an x, an x to the second, x to the third, x to the fourth, x to the fifth, but you can even skip terms and so forth. But yeah, you're right to make that connection. So keep that in mind. We'll keep talking about that. So these are equal if, and again, you could say the interval of convergence. This is one way you would write it as I wrote it above. Or you could also say, because that's 0 out to 6 and 0 down to -6, you could also say this has a radius of convergence equal to 6. I mean, those are two ways of saying the same thing. And you can see that's important to note, right? So that's kind of crazy. So it's so these are actually equal, but just with some conditions. So the other thing that's important to kind of point out is notice the equation that I happen to pick. You agree that the equation I happen to pick here just kind of happened to look a lot like this, right? Like what if I picked like the sine of x? Y equals the sine of x. Well, the sine of x does not look anything like a over 1 minus x. So we got a ways to go here, but believe it or not, we're going to get to sine. And logarithm and tangent and every other crazy function that you could possibly imagine. Again, this should just strike you as neat but irrelevant. But remember, and I'll encourage you to play with this on your own, if those two functions are actually equal, does it make sense you could take the derivative of the left side? And you might remember, oh yeah, quotient rule. Boy, that was ugly. The derivative of the left side is going to match the derivative of the right side, and the derivative of the right side is really easy. Does that make sense? It's just power rule. So believe it or not, that would be a way of actually making new functions, if you will. Or the integral. Couldn't I take the integral of both sides? That's kind of terrifying on the left side. A fractional integral. Remember how that was like integration by parts? And oh man, this is horrible. Not the right side. Super easy integral to take. This is the reason why we know the integral of sine is or the derivative of sine is cosine. But anyway, we'll get down that road. The point is the blue equation in the real world is easier to work with, even though it's an approximation, because in the end you can't go forever, right? You got to stop at some point. You got to say, all right, I'm going to take it out to x to the 7th, then I'm going to quit. But then I'll use the right one to make an approximation for something because maybe the left one is more trouble. And keep in mind, right now the left one is not trouble, but when it's logarithm, it will be. Can you appreciate ancient people that didn't have a logarithm button on their calculator and they wanted to know the natural log of 8? Does it make sense they could have actually found it using arithmetic on the right? Do you understand the profound nature of what I'm saying there? Like no arithmetic is going to get you the natural log of 8. But if we could find an infinite series like this that was just a polynomial, then you could just plug 8 into that equation right there, and just using a cheap, $5 calculator that does add, subtract, multiply, and divide, you could know the natural log of 8. So that's part of what makes this concept profound. Well, let's do another example. I'm going to try out my new discovery. Duplicate. Oh my gosh, I'm so dumb. Why can't I read? Should have been doing that all the time. So I'm just recording this again so that we can use it. But let me give you another example. That's, well, this time slightly further away from looking like that. So today, and really in chapter, and it's surprising how far away from that we can get, but let's play with this just a little bit more. Let me give you another example. What if we had this example? F of x equals 2x over, let's say, 3x minus 8. Would you agree that x on the top is not good? Because our expression has just a constant on top. It's just got a constant up there, right? So that a represents a constant. And unfortunately, now we got an x up there, so that's not good. How are we going to get this? How are we going to get this to look like this so that we can then expand it and write it out as a power series? Again, I want to use that language with you. It's called a power series because it's x to the first and then x to the second and x to the third. Those are power equations, not exponential. It's not, the x is not in the exponent. The powers are numbers, and so that's a power series. Now that we're not looking at this just as numbers, we're now looking at this with x in it as a letter and not as some number like 3/4 like on your test. So can we get that to look like the form it needs to be in? The answer is, well, of course, or I wouldn't be showing it to you. Would you agree that I could just pull this x out front? For the future, why do I not care that there's an x out front? why could I just kind of like cover that up for now and just sort of pretend it's not there? And then proceed with something that now does look quite a bit like it's supposed to look like. Why? I can't erase it, but what am I going to do later on once I have it expanded out to that?
Just multiply an x by everything.
Just multiply it all by x. Like all of them are just going to go up a power. Does that make sense? Like so it's okay that there's an x there. I mean, it can't be there for the problem, but if I pull an x out, so for that reason, it could be x cubed, x to the fourth, it could be anything. And I could just pull it out front and kind of just worry about it later. Do you see why this is going to be okay? So, okay, great. I pulled an x out front. And again, now I got to get it to look like what it's supposed to look like. So you know, I need a 1 in front. Well, I'm going to rewrite it so the 8's in front and the 3x is over here. And what am I going to do now? What's the important thing I got to get? I don't care if the top is a 2. I don't care what's up there, but what's really important that just happened a minute ago that needs to happen again?
You gotta divide by -8.
Beautiful. Got to divide everything by -8 because I need this to be a 1. So divide by -8 because I need that to be a positive 1. So if I did that top and bottom, then I could say my function of x now is equal to, let's see, that'd be 2 over -8, which is -1/4. -8 divided by -8 is 1. Mission accomplished. And then this would become minus 3/8 x. Boom, we're ready. We got it now. So our a is just -1/4, and our x is 3/8 x, if you will. It's kind of a weird way to say it, but notice again, don't ignore this, but that's a minus sign, and it's a minus sign. Like that's not -3/8. You understand that? That is a minus sign, and that's a positive x. Well, now it's a minus sign, that's a positive 3/8. So I'm treating that as just a 3/8. So maybe I should say the x turns into 3/8 x. And so, okay, I think I know what this expands to. So then I can say f of x then is also equal to the infinite sum where, let's see, there's an x out front. I haven't forgot that. And the a, all I'm doing is just staring at this statement right here, right now. The a is -1/4, and it's x to the n power. Well, n goes from, and again, notice it's from 0 to infinity. You don't have a choice. Remember, that only worked. Somebody screwed that up on the test. It only goes from 0 to infinity. And but this time, what's my x? It's not just x, it's 3/8 x. Now, let's play with that a little bit, because it's kind of unwieldy right now. And there's two things I could do here. One of them is try to simplify that, because, you know, I got x over here and I've got x over there. And so could I kind of clean that up a little bit? And, you know, could the 3/8, like, where does the 3/8 go? And, or the other thing is I could just expand it, like, and I find myself thinking, let's just expand it first. So let's see, what does this thing look like if I were to expand it? Well, when n is 0, that'd be 3/8 x to the 0. That's just 1. And then I'd have a 1/4 and an x. And so my first term would be -1/4 x. You agree with that? Again, slow down, disagree. If you're wrong, fine, we'll all fix it. Now I want x to be 2. So let's see, that'd be x. There's the x out front. There's the -1/4. And now I have, I'm sorry, I said 2. We just did 0. So this is now 1. 3/8 to the 1. So we have 3 times 3/8 times x. And so I end up with a minus sign again. The minus sign didn't go away. And I have x times x squared, and I have 3/8 times 1/4. That'd be 330 seconds. I guess I can't reduce that, so it's 330 seconds x squared. Now n is 2. What happens now? Well, now that n is 2, this just becomes a 3/8 squared. And so now I have x squared times x, which is x cubed. And I have 1/4 times 3/8 squared. That'd be 9/64 times 4. 64 times 4 is 256. So it's minus 9/256. So that's what it expands to. So just to make sure this is working, I'm going to go over to Desmos now and see if these are looking the same. Like I don't need my open math or somebody to tell me if I got this right. I'm going to go see if these are looking the same. I'm going to use the place where I can copy and paste. This isn't quite as good because I can't save a copy of it, but our original equation was y equals 2x divided by 3x minus 8. So again, this has an asymptote sort of a look to it. And now I'm saying, hey, I have this second equation now that, and again, let's watch it grow. Y equals first negative 1/4 x. Do you see that we're seeing the same thing as last time? In other words, where do they look the same? They look the same at 0. And then my next term was minus 330 seconds x squared. I'm going to do this a little different this time. Do you see how it's just that much better? Like the black one is the right answer, right? The black graph is the actual graph. We did the red graph and it was good, but notice the blue graph better. Closer, right? Let's do it again, except for our next term was minus 9 divided by, I keep hoping I'm making a math mistake here someplace just so you can see how to catch if you did something dumb. Ah, even better. Isn't this exciting? Look at that. The green graph is even closer. You see it trying to follow it? It's just getting better and better and better. Now, let's use that to get the next term rather than punching calculator buttons. Again, let's do what I did a second ago. Let's see, what is this? It was always a fourth. So it was minus, and there was always a fourth. But then it got multiplied by 3/8 to a certain power. Does that make sense? So it was times 3 divided by 8. And that was raised to a certain power. And it's the power, let's see, is it the power we're on? Yeah, we're on the 4th. So it's to the 4th power.
I think it should be third.
You think it's one less? I hope I'm wrong. I hope you're right. Actually, I meant to not. So I like my gut reaction, it was supposed to be the 4th, but maybe I'm getting this wrong. It doesn't look like I'm wrong, because do you agree it's better? Do you see how they keep getting better? Black's the ideal, red was the next, blue was better, green was better, purple was even better. Let's see, so this was 3/8 to the 1st. Yeah, you're exactly right. It's too high, isn't it? Raymond is right. It's not to the 4th, it's to the 3rd. So notice my graph didn't tell me that, but watch what happens to the purple graph. See how it just got better? That was supposed to be to the third power. The reason it's, why did I get that wrong? It's kind of an understandable mistake. Why did I get that wrong?
Because you thought that you started at n equals 1.
Couldn't be said better than that. Yeah, I started at n equals 1. In other words, this was actually 3/8 to the 0, 3/8 to the 1, 3/8 to the 2, 3/8 to the 3. Okay, so we're going now. So armed with that, does it make sense? It starts to get easy for me to add terms now. All I have to do is copy that whole thing. And I can just say 3/8 is now raised to the 4th. And this x is now to the 5th. Now I just have one better term. Notice it switched back to black again. I'll change that in a minute, but you see how it's just getting better? Isn't that cool? I'm going to change it right now. You run out of colors at some point here, but now again, if I kind of get back away again, if I just look right in here, notice it looks really good. They kind of all look good right in here, but notice they stop looking good. Like notice at 2, they don't look good. Remember, like last time it was from 6 to -6. It isn't working here. It's not going to 6. What's it going to? Like when do these look the same? Again, I'm gonna add another term to this. I think I'm gonna go back and turn all these off now just so you don't get confused. I'm gonna add one more term to this. This now goes up to the 5th. This now goes up to the 6th.
Your 5th kind of is in the wrong spot.
Thanks. Supposed to be an exponent. So they look good. I think you'd probably agree we're looking good out to 1.6. But then it's like not so good. Like, is 2 okay? Well, maybe 2 would be okay if I added more terms. But by the time you get to like 3, they're clearly it's not really working anymore, right? Like they're blowing up. It's like it's not really working that great now. But the point is, you can see it working, and you should be doing this, especially with your first assignments, like graph it on Desmos. You should be able to watch it work. Again, this is going to get better later because right now we have these limitations to this, but we won't later on. So I want you to remember where this doesn't work. Well, notice the asymptote here. Where's the asymptote for this graph, the black graph? Where does it freak out because of the equation 2x over 3x minus 8? What can x not be? Well, when is 3x minus 8 equal to 0? It's not so easy just to see it in your mind. You got to solve it like an equation. When is 3x minus 8 equal to 0?
When it's 8/3.
Yeah.
Exactly, 8/3. So let's go have a look at this. Well, so we succeeded in writing out this first term, but let me add one other thing. So let's try to write this is like option 1 kind of expanded. Option 2, let's call it improved sigma. Like, could I write that sigma statement any better, any cleaner? Well, I guess I could say there's an x there, there's a -1/4 there, and then I can, let's see, do I want to do that? I don't think I do.
Would pulling the 1/4 out in front of the sigma notation be a bad idea?
No, it isn't. Like, it doesn't hurt to pull the 1/4 out since every single term is multiplied by it. Doesn't hurt a thing. trying to decide if this is gonna make our life any better. Well, let me say this with respect to the radius of convergence. Again, do you agree that the junk, if you will, right there, this junk right here, that's what's got to be less than 1? Isn't that what we're always saying? We're saying that junk right there has got to be less than 1. Except for, what is that in our case? In our case, it's 3/8 x. Well, 3/8 x has got to be less than 1. Well, notice if you multiply by both sides by 8/3, there's your radius of convergence. In other words, it was 2 2/3. If you're not going to get past 2 2/3. They'll look the same as long as you stay
See, I thought
between
the,
2 2/3 and negative 2 2/3, if I'm technical about it. Go ahead, Raymond.
I thought that the radius of convergence would be 8.
No, because of the 3. The 3 is part of it too. In other words, that whole statement inside there is what's got to be less than 1.
Oh, okay.
So technically, I would say absolute value. So you could say the radius of convergence is 8/3, or you could say the what did I call it? I also forgot. The interval of convergence. So the radius is 8/3. The interval of convergence. So they'll look the same, but only between there. Again, that's very disappointing, right? It means, well, they're only the same, but they're the same, but you can only plug in 1 and 2 and 0. You can't plug in 3, you can't plug in 4. Well, you know, what good is this? Not as much good.
So Doug, back on the previous question when we had x over 6,
Yeah.
do we always treat x's as 1s? Because I think that radius was it -6 and 6?
Yeah, but that's because, again, what was inside here? It's the absolute value. If I go back and add that in, it's the absolute value of whatever you see sitting right there has got to be less than 1. Well, I just solved it for x. And in this case, I had to multiply by 6 to do it. So that's what gave us a radius of convergence of 6. So it's whatever's inside there with the x, whatever's in there being raised to the nth power, just like in our statement. Just like in our statement here, whatever's right here, if it's not just x, if it's 6x or 8/3 x or whatever's sitting right there has got to be less than 1. And so that's what allows you to kind of see what the radius of convergence is.
But you actually solve for it like that, because couldn't
Yeah.
x have been anywhere from 1 to 5 and it would still be less than 1.
That's right. Right now, what we're looking at is things that are always matching up at 0, but we'll take it outside of that realm in a little bit.
Okay.
Let's look at one more example and then we'll be done. I'll try to go a little faster with this one so we don't run out of time. And we got some that look really weird to do in this section, but we'll be getting to those tomorrow, like logarithm. I'm going to show you logarithm tomorrow. We'll run out of time today. But I'm sticking with stuff that looks at least reasonably the same. And so let's consider this one. This isn't terribly far off. So it still has that same type of a look. And you probably feel okay about the fact that I could pull x squared out in front, because that's what we just did a second ago. In other words, multiply every term by x like we did last time. We had an x pulled out in front. Well, notice our equation, if you will, did not start at, well, a constant. You know, we're used to it starting at a constant. Well, it started with x because we multiplied everything by x. So the fact that I need to pull out x squared here, that's no problem. I'll just multiply by x squared. So that means my first term will be x squared, and then I'll have an x cubed, and then I'll have an x to the 4th. So that's okay. But would you agree that this this squared right here Like, uh-oh, you know, is that going to be a problem for us? The answer is, well, no. Again, you might say, hey, this looks good, except for that 6 needs to be a 1. So I need to divide by 6. So if I do, I'd have 5, 6 on top. I'd have the 1 there that I need. I already have a minus sign. Very glad that's a minus sign. And then I got to divide 24 by 6. Unfortunately, that comes out a whole number this time. So does that look enough like it that I can just say, good, I'm ready to go now? So if you will, as I said before, your A value is 5/6, and your sort of your X term is actually, well, that whole mess. X is, instead of X, it's just 4x squared. Can I just, whatever's sitting there, there's a 4, there's an X squared. The answer is yeah. So what you're saying is that our function then, which we started out saying it's this, you know, crazy squared equation, and, you know, we might wonder, what does that look like if I graph it and so forth? We'll do that in a minute. But we're saying that it could also be written as, and again, all I'm doing is staring at this statement that we had before, that red statement right there. I'm just rewriting it. I'm going this direction. A x to the n, that's it. So A is 5, and there's an x squared out front. I can ignore that. So A is 5/6, and that is multiplied by x to the n, where n always goes from 0 to infinity. It's just that what's my x in this case? Oh, it's that whole mess right there, 4x squared. Let's see. So what does that expand to, just to kind of see, you know, what does it look like if it's kind of nice just to see the terms written out, see a little bit of a pattern to it.
Jason Adams.
Okay. So let's see, when n is 0, then that means this whole term would just be 1. So I just have 5/6 times x squared. And when n is 2, I'm sorry, n is 1. When n is 1, I'd have 5/6 times 4. So that'd be 20/6, or 10/3. And I have 4x squared times x squared. So that'd be 4x, no, sorry. That'd be, I already took care of the 4. So I have x squared times x squared. That'd be x to the 4th. Okay. When n is 2, let's see, I have x squared times 5/6 times 4x squared. That'd be 4 squared, which is 16, and x squared squared, which is x to the 4th. So I guess that's 16/6 times 5, or 8/3 times 5. That'd be 40/3. And then I have x to the 6th. So I can see the pattern, like my next term is going to be x to the 8th, and my next term is going to be x to the 8th, and, you know, and so on and so forth. I just have to kind of work out what the constant is. And as we did a minute ago, in the end, what's this constant right here? I'm sorry, I wrote that wrong. We already had a 6th, and so this next term is 8. And then this next one out here, of course, would be 10, and so forth. So I can see that those are going up by 2. Why are they going up by 2? Notice there's like none of the, why are they, how come there's no 5th degree? And what's causing there to be no 5th and 7th and 9th? What's causing that?
Is the x squared that we have in front of it.
That's exactly right. That squared right there is what's causing that. So let's see, what is this? This term is really 5/6 times 4 raised to what power? Well, this was 0, 1, 2. This is to the 3rd. It's really 5/6 times 4 to the 3rd. That's what's going to go in there, whatever that fraction is. This will be 5/6 times 4 to the 4th, that's what's going to go in there. That's the advantage of sigma notation. In other words, I don't have to figure out each coefficient without a pattern. There's a pattern to those too, 5, 6 times every single one of them. And again, you can pull 5, 6 out in front of this whole thing and not even have that. And that'd probably look better. Do you agree with that? Maybe I'll write it that way really fast. 5, 6 times everything. So that'd be x squared. And then this would be just 4. Yeah, 4x to the 4th plus 4 squared x to the 6th plus 4 cubed x to the 8th. See how much easier it is? Plus 4 to the 4th. I think that's 256 x to the 10th. So see how much nicer it is to pull that fraction out front. It makes the coefficients more recognizable, if you will. So I'm just looking at it and saying, okay, cool, that makes sense to me. Let me show you something though, it's kind of cool, and then we'll be done. The improved sigma. Let's try to write that a little bit differently. So let's see, we have x squared, and we have 5/6, and then we have 4x squared n. Would you agree that that could be written as, and this is actually important that we do this, 2x to the 2n? How did I get that? Well, I just noticed that 4x squared is the same as 2x squared. And don't you, if you have exponents, 2 exponents, like I've said before, if you have like x to the 2nd, to the 3rd, don't you multiply those and that becomes x to the 6th? So that'd be the same as 2x to the 2n power. Now that that's not squared, do you agree that this right here is what's causing our radius of convergence? So the absolute value of 2x has to be less than 1. Wow, this has a really small radius of convergence. So the absolute value of x actually it has to be less than 1/2. So 1/2 is our radius of convergence. Whoa, you mean we can't even plug 1 into this? These aren't the same unless you plug something in that's between 1/2 and -1/2. Yeah, that's what I mean. That's useless, if you will. That's not that cool. Or our interval of convergence, we would say x has to be between 1/2 and -1/2. That's kind of a bummer. Perhaps you even notice, this is just a side note, but perhaps you even notice that you could even collect the x squared and the 2x. What if you take x squared and you multiply it by 2x to the 2n? What happens if you put those together? Can I put those together?
Are you trying to add the exponents?
Yeah, I can add exponents, but the bases aren't the same. Do I care? Do I care the bases aren't the same? In other words, if you had like x to the 2nd and y to the 3rd, can you add the exponents and have something to the 5th? You know, something like that? The answer is no. The bases do have to be the same, so that's a bit of a problem. So can I make any progress with that? Well, would you agree that this is true? Couldn't I just split them apart? Split the 2x? So it's 2 to the 2n and x to the 2n. Now these can be combined because they have the same base. And so I could say I have 2 to the 2n times x to the 2n plus 2. That's sort of one option. If I want it to be all under the same, this is tricky though, you have to think about this. If you want them to be all, can I have like a +2 here? Could I have a +2 there? Could I just, I mean, that'd be cool, right? Because if I had a +2 there, then couldn't I say this is 2x to the 2n plus 2? Now they're all kind of under there together. What did I just do though? By adding that 2, what did I really just do?
Did you just move the sequence of numbers?
You added 2 terms, right?
I mean, if I added a 2, isn't this what it would have done? In other words, to do that, I effectively had to multiply by 4. Is it okay just to multiply by 4? Well, yeah.
Yep. As long as we divide by 4,
As long as you divide by 4.
there's no equation.
So that means our, cleaned up, really nice looking improved sigma would be 5/6, but I would have to divide by 4, making it 5/24. And then I could write this as 2x to the 2n plus 2. Mo better. Is that worth the trouble? Not really. Like, not to expand it. That's pretty dangerous, right? But to check my work, which I'm not going to do because we're out of time, I could expand this. In other words, I'm sitting here wondering, is that right? Like, did I get this right? Well, I could stick in as 0, get an answer, stick in as 1, get an answer, stick in as 2, get an answer, and just kind of make sure that, it's the same as it was. And it is in this case. So I'll leave you to think about that, but that's kind of cool, I guess. It's a cleaner way to write it. So quickly going out the door, let's graph both of these. And I'm going to kind of focus on that the red one up there. I'm going to go back to the original, graph that equation right there, and then I'm going to graph this red one, just expanding all the terms out. And then we'll call it a day. So our original problem was 5x squared. Oh, 6 minus 24x squared. So again, what we're going to get is a graph that looks the same right in here somewhere. Because we're at 0, we're centered at 0. That'll make some sense to you later on. So my first term was 5/6. That was times x squared. So just to save time, I'm going to leave it like this. So it's working, right? Like, ooh, it looks good. It already looks good. Notice it looks good, well, maybe out to like 0.2. Starts to not look good later on, but let's add our next term. Our next term is 4x to the 4th. So if I add to that, watch it get better. Plus 4x raised to the 4th. Whoa, yeah, look at that. Now it looks good out to maybe a 4th. Before it was like 0.2, now it's out to a 4th that it looks better. Let's add another term, plus 16 x to the 6th. I can't seem to type. Oh yeah, look at that, looks even better. Now it looks good out to like 0.28. Let's add one more term and let's automate the process a little bit. What's my next term? It's 4 to the third. Well, I don't know what that is. I can't figure it out in my head. So I'm just gonna write it in there. X raised to the 8th. Yeah, it's looking good. But what's the best we're ever gonna get? What did the radius of convergence just say a second ago?
0.5.
0.5. Notice it's not that good yet, right? 0.5 is a tall order. So if I copy this, add a few terms to it, and let's see, this is going up to 4 to the 4th. And this is now to the 10th. This is 4 to the 5th. This is 4 to the 6th. This is 4 to the 7th. This is X to the 12th. This is X to the 14th. This is X to the 16th. See how it's just getting better and better and better? You can see it's working its way to 1/2. Remember, when you get really close to 1/2, if you tried to plug in like 0.49, like that's too close to the boundary. Remember how 1 over X just barely diverged? The harmonic series barely diverged, but 1 over X to the 1.1 because of the p-test converged. Well, if you get close to the edge of it converging, that's not a good number to plug in. You're going to need a lot more terms than this. So what we're seeing here, at least visually, is that, yeah, if you stick to like 0.4, if you said, you know, let's do this really quick. If I said f of 0.4, so I said, what does that top equation give if I put in 0.4? Well, the answer is 0.37. If I call this equation g of x, and I said, well, what's g of 0.4? Notice I get reasonably similar answers. One's 0.37, one's 0.36. That's not too bad. But of course, if I, go out to like 0.46, now all of a sudden they don't look so good anymore, right? Because I'm pretty close to the radius. That's the idea. Okay, so you are prepared now to do all but the last maybe 3 or 4 questions in the assignment if you wanted to start on 11.1. The last few, though, require some stuff, and that'll be tomorrow's discussion. Really brilliant ideas that you can use to actually make progress. We're going to do natural log tomorrow. That's going to be awesome. How do you replace natural log in this way? Like, that seems impossible. So we'll play with that tomorrow. I would encourage you actually to try to do that part of the assignment before tomorrow, just because it'll probably help deepen your understanding of what I've showed you today so that tomorrow will make more sense. All right, stay after if you want to discuss something as always. Otherwise,
Thanks, Doug.
you all.
All right. Bye, Doug. Thanks.
I had a question.